This video is on section 8.5, which involves partial fractions. Before beginning this lesson, I would highly recommend taking some time to research or remember how to perform partial fraction decomposition. It's a topic that's taught typically in Algebra 2 or pre-calculus. But take a moment before watching these videos to kind of refresh your memory on that in order to avoid some confusion. So partial fraction decomposition is helpful when integrating. For example, maybe you're given something like this. And if you're given a problem like this, there are a few ways in which you can integrate it, one being much easier than the other. Take, for example, attempting to integrate this without the use of partial fractions. If you attempt to integrate this without partial fractions, what you'll need to do is you'll have to complete the square and then use trig substitution in order to come up with this. Once you get here, which requires quite a bit of work from previous sections, once you get here, you continue on and integrate with respect to theta. However, we don't want theta, so we have to make a substitution that involves x's rather than thetas. And you can see all of this work that it takes in order to get to this simple answer. Now suppose, on the other hand, that you observed the following. Suppose you remembered partial fraction decomposition from way back when, and you were able to rewrite this fraction as this combination of fractions. If you were able to make that observation and come to this conclusion here, you would be able to integrate these fractions individually and come up with the exact same answer that you would have found in the previous slides. Clearly, much less work is involved. So with that being said, it's preferable to apply partial fraction decomposition whenever possible because it makes things much easier. So I'm going to kind of very briefly try to remind you of how partial fraction decomposition works, and then we will apply it in integration techniques. Let's say we have this polynomial here, and we want to factor it because we need to be able to factor successfully in order to apply partial fraction decomposition. Remember, anytime you have 4 terms in a polynomial, you can factor by grouping, which is essentially what they are doing here. So remember, when you factor by grouping, you take out a GCF from each of the factors. Then your common factor, you must have a common factor, becomes one of the factors, and then anything that's remaining becomes the other factor. Then this is a difference of 2 squares. This difference of 2 squares can be rewritten like this, and then the final factor cannot be factored any further. Then this is a difference of 2 squares. That can be factored further here. So you can see that we have one repeated linear factor here. We have one quadratic factor and then this linear factor also. So this is what we will need in order to proceed with the partial fraction decomposition. So if you look at this, here is our polynomial, And here we have all the factors that we have found. Oops, sorry. Now, remember, we want to split this up into different fractions. And this is the part you might want to review. So each of the linear factors has just a constant above them. So notice that these are all linear. As far as the repeated fraction or the repeated factors, you need to have both this and this. So if this were cubed, you would have x plus 1 squared, and then x plus 1 cubed, all as your fractions. So you need each one of those. And then if you have a quadratic factor, then you need to have a linear factor above it. Okay, and our goal is to identify what constants are for A, B, C, D, and E in this case. Okay, very briefly, here are the steps that are taken when applying decomposition of partial fractions. So you can take a moment and read through this, but I'll show you some examples and hopefully you'll remember some of this. So let's go ahead and get started now. So here in this example it says use partial fractions to find the indefinite integral, which is given here. So the first thing I need to do is I need to look at the denominator and I need to factor that. So you might want to pause the video for a moment and see if you were able to successfully factor this. When you factor this, you should end up with factors of x plus 4 and x minus 1. These are the factors that we'll use when rewriting this polynomial. So this is equivalent to 5 over the quantity x plus 4 times the quantity x plus 1. So remember, what I want to do is I want to break this down into each factor. And above each factor, we will have some constant. We'll call this A and this B. And our goal is to find out what A and B are equal to in order to apply the integration. So what I need to do is I need to eliminate the fractions here. And the way I'm going to eliminate the fractions is by multiplying everything by this common denominator here. When I multiply everything by this common denominator, I end up with 5 is equal to A times the quantity x minus 1, because the x plus 4's cancel, plus B times the quantity x plus 4, because the x minus 1's cancel. Once I have this, what I want to do is identify some values for x that will be able to be substituted in to eliminate something. For example, when x is equal to 1, so I have just chosen this value, okay? And you get to choose these values also. When x equals 1, if I were to plug 1 in here, then I end up getting A times 0 plus B times 5, because 1 plus 4 is 5. And you can see the reason I chose 1 is because I wanted to multiply by 0 in order to cancel that variable out. So if I were to solve this, I have 5 equals 5b, divide both sides by 5, and I will have found that b is equal to 1. So at some point I will substitute this 1 in for b here. Now I'm going to make another suggestion, and I'm going to say, hey, let's let x equal -4 now. And the reason I've chosen -4 is so that this b term can cancel out. So when I plug -4 in, I have 5 is equal to a times -5 plus b times 0. And again, this will cancel out. So I have 5 is equal to -5 times a, divide both sides by a -5, and you will see that a is equal to -1. So now I know what constants a and b are, and so I can rewrite this integral. So the integral that we started off with was this. But I know that this is equal to this. -1 over x plus 4 plus 1 over x minus 1 dx. Because they are the same thing. Now if you want, you can write this as separate integrals because they're separated by this plus sign. So you can integrate each of these separately. When you integrate this, you end up with a negative natural log of the absolute value of x plus 4, and then plus c, of course. Over here, you end up with plus natural log of x minus 1, and then plus that constant of integration. In this case here, you can use properties of logarithms to combine these, and you will end up with the natural log of the absolute value of x minus 1 over x plus 4 plus c. And that is the final answer. Let's just keep hammering away at examples here. So looking at this, we will need to factor the denominator only. So you may want to take a moment and see if you're able to factor this. This, you can take out a GCF. And then once you do that, the remaining quadratic can be factored further into x plus 1 times x plus 1, which is the same thing as saying x times the quantity x plus 1 squared. Okay, so what we're going to do is rewrite this fraction. So I still have this numerator, and this denominator is now going to be written as x times the quantity x plus 1 squared. Now this is going to be broken into 3 different fractions. The first one is going to be x. Since this is linear, we will have an a on top. Then this quantity is going to be broken down into x plus 1 as the denominator of one fraction, and the quantity x plus 1 squared in the other. Both of these factors are linear, so we will simply use constants in their numerators. Okay, so this is how we will break this up. Now, what we need to do is we need to identify what a, b, and c are. And the way we attempt that is we're going to multiply everything by the least common denominator. So I need to eliminate the fractions. So I'm going to multiply everything by this. So I am left with the numerator is equal to a times x plus 1 squared plus b times x plus 1 plus c times x. Now what I'm going to do is I'm going to analyze each of these, and I'm going to choose different values for x. So when x equals -1, for example, and again, I have simply chosen this. Now, the thing that is different here than the first example is before we just had a 5, so there weren't any x values to plug this into. But here, we need to plug this into every place we see an x. Okay, so I'm even going to plug it into the left-hand side. So when I do that, I end up getting 9 on the left-hand side. And you can go ahead and check that. If I plug a -1 in here, this all goes away. If I plug a -1 in here, this all goes away. So I'm going to plug it in here, and I end up with 9 is equal to -1c, which tells me that c is equal to -9. Okay, let's pick another value for x. X equals 0, for example. Go ahead and plug 0 in everywhere you see an x. When you do, you end up with 2 is equal to, if you plug in 0 here, you get 1 times a. If you plug in 0 here, all of this goes away. If you plug in 0 here, all of this goes away. So that was quite easy. So I found that a is 2. So now think of some other value you can plug in. Now this gets a little tricky because there aren't any values that will completely eliminate a term. But you already know A and C, so we need to find B, and we can use these values to help us. Let's let x equal 1. If I let x equal 1, I plug in 1 here, and I end up with -3 on the left-hand side. If I plug 1 in here, I end up with 4a plus. If I plug in 1 here, I get 2b. If I plug in 1 here, I get c. Okay, well, I know a and I know c. If I know those values, I can plug them in and find b. So -3 is equal to 4 times 2 plus 2b minus 9. All right, so this is 8 minus 9, so -3 is equal to -1 plus 2b. Add 1 to both sides, and you should find that b is equal to -1. So I have found A, B, and C. On the next slide, what I'm going to do is I'm going to rewrite this integral as these separate fractions. So here we go. This is the original integral that we had. And with the work that we have just found, we know that this can be rewritten as the following integral. 2 over x, because we found a to be 2, minus 1 over x plus 1, because we found b to be -1, so I just wrote this as a negative fraction instead. Same type of thing here, minus 9 over the quantity x plus 1 squared. So now what I can do is I can integrate each of these fractions individually. So when you integrate this first fraction, 2 over x, this becomes 2 times the natural log of the absolute value of x, minus this one becomes the natural log of the absolute value of x plus 1. This one here, if you want to use a u substitution, you can. U is equal to x plus 1. If that's the case, then du is equal to 1 dx. So you can integrate u to the negative power of 2. When you do that, you get u to the negative power of 1 divided by -1. So when all is said and done, after integrating this, you should end up with plus 9, because you'll have a double negative, plus 9 over x plus 1 plus that constant of integration. If you want, you can go ahead and combine these using the properties of logarithms. So remember, this 2 can become an exponent here. So this will become the natural log of the absolute value of x squared over x plus 1 plus 9 over x plus 1 plus c. And that is your final answer. Moving right along to yet another example. Okay, so here, just like before, we want to factor the numerator. So when I factor this, the denominator. When I factor this, this is a difference of 2 squares. So I know that this factors into 4x squared plus 1 times 4x squared minus 1. Now, this first factor cannot be factored any further. However, this is a difference of 2 squares, so this can be factored further. So keeping our first factor and factoring the second into 2x plus 1 times 2x minus 1. That is the complete factorization of our denominator. So just like before, we will rewrite this fraction as x over, I'm going to write the linear factors first, 2x plus 1 times 2x minus 1 times 4x squared plus 1. Okay. Now, these 3 factors, none of them are repeated. In other words, none of them have an exponent. None of these are raised to some power. So I will have only 3 fractions, which are these fractions here. The difference is now we have a quadratic. So above each of these, we will have a constant, but with a quadratic, we need this. Okay, so that is something that you should try to remember from your previous classes. Now, all the following steps are the same. Everything beyond this is the same. So we need to eliminate the fractions, choose some values for x, and find the values for a, b, c, and d. You might want to consider pausing the video and see if you can attempt to do that. So I'm going to multiply everything by this denominator, and I will get the following. X is equal to a times 2x minus 1 times 4x squared plus 1 plus b times 2x plus 1 times 4x squared plus 1 plus c times, cx plus d times 2x plus 1 times 2x minus 1. Okay. Now, what we need to do is try to cancel some things out. So let's let x equal a half. So when x is a half, I need to plug a half in anywhere I see an x. Okay, so when I do that, I have 1/2 is equal to, the a term cancels and the c term will cancel. So plugging it in here, I end up with b times 2 times 2. Plugging it in here and here. So I have 1/2 is equal to 4b. I'll divide everything by 4, and I will find that b is 1/8. I'm going to do the same type of thing when x is equal to -1/2. So plugging that in, I have -1/2 is equal to, well, when I plug in -1/2, all the b term cancels out and all of this term cancels out, leaving me with a times -2 times 2, which is -1/2 is equal to -4a. So a is equal to -1/8. Okay, so now we know a and b. Let's truck along and let's let x equal 0. That's always a nice choice. So when x equals 0, I will plug 0 in everywhere. When I do, I end up with a times -1 times 1 plus b times 1 plus, if I plug 0 in here, this goes away. So I'll have d times -1. All right, so here I end up with 0 is equal to -1 times a gives me a 1/8. Plugging that in. b times 1 hang on here. My bad. Let's go back. I apologize. This should be a positive 1/8. Sorry, that's where I went wrong. So this is a -1/8 plus 1/8. I apologize, right here, minus d. So these cancel out, so we find that d is equal to 0. Sorry for the error. A negative divided by a negative is positive. So now we can proceed, and the only variable we need to find now is c. So let's let x equal 1. So if x is 1, I'll plug 1 in everywhere. And when I do, I end up with a times 1 times 5 plus b times 3 times 5 plus the quantity c plus d times 3. Okay, well, this becomes 1 is equal to 5a plus 15b plus 3c plus 3d. So now we're just going to substitute things in that we know. D is 0, so we know this goes away. So I have 1 is equal to 5 times 1/8 plus 15 times 1/8 plus 3c, which is what we need to find. Now, I'm going to let you go ahead and finish this math and identify that c is -1/2. So just trying to save some time here. All right, so we know A, B, C, and D. On the next slide, I'm going to set up the fraction so that we can see what it looks like. Now, when we set this up, I'm going to, instead of putting 1/8 here, I will put 1/8 times this quantity. Okay, so I'll show you what that will look like. Here we go. So the original integral was the following. Well, we end up with 3 separate integrals. The first one is 1/8 times 1/2x plus 1. Okay. The second is the integral of 1/8 times 1 over 2x minus 1. The third integral is the following. It is a negative 1/2 times x over 4x squared plus 1. Now remember, d is equal to 0, and then c is negative 1/2, and so that's why that integral looks the way it does. Okay, so now we are going to integrate each of these separately. And when we integrate these, you certainly can use a u substitution. If you use a u substitution here, you would let u equal 2x plus 1. So then du is equal to 2 dx. So when you do that, you will end up with integrating 1 over u du, and you'll get 1/2. So taking this constant out, I think you can do the u substitutions yourself, but we will have this 1/8 times 1/2 natural log of 2x plus 1. Then for this one, you can also use a u substitution. 1/8 times 1/2 times the natural log of the quantity 2x minus 1. Over here, this one will be a little more complicated with the u substitution. Here you may want to let u equal 4x squared plus 1. So then du is equal to 8x. So you'll need to put an 8 in and undo it on the outside. When all is said and done, you should end up with plus this negative 1/2 times 1/8 times the natural log of the absolute value of 4x squared plus 1 plus the constant of integration. So cleaning this up, let's just combine these. So I have 1/16 and another 1/16 minus another 1/16. Okay, a couple things. Since these have the same base and they are being added, we can combine these two as the natural log of 2x plus 1 times 2x minus 1 using properties of logarithms, minus all this. And then if I want, I can FOIL this out, or combine this. Yeah, so FOIL this, and when I do, then I can write these two logarithms as a single log. So when all is said and done, I end up with the following. Which is this over 4x squared plus 1 plus the constant of integration. And that gives you the final answer. Here's the last example that I will show you, and this one's going to take a little bit different method once we are trying to identify the values for A, B, C, and so on. So make sure you watch this example because it will be a little bit different. So the first part is basically the same type of thing. We need to factor this denominator. So you may want to see that you can factor this. This here factors into x squared plus 4 times x squared plus 4, which can be written as the quantity x plus 4 squared, which is a little bit different. So when I rewrite this fraction, I keep the numerator, but the denominator is going to be rewritten as the following. Now, I need every factor of this, so I'm going to end up with two fractions. One is x squared plus 4, and the other is x squared plus 4 quantity squared. Now, each of these factors are quadratics. Since these factors are quadratics, that's going to change what my numerator looks like. So here I will have ax plus b, and here I will have cx plus d. So that is one thing that is different. Now, in this case, we will continue to proceed the same way as the previous examples. So I need to eliminate the fractions, and I will eliminate the fractions by multiplying everything by this denominator. So I end up with x squared plus 6x plus 4 is equal to the quantity ax plus b times x squared plus 4 plus cx plus d. Okay, now what I'm going to do is I'm going to FOIL this. So when I FOIL this, I end up with the following. I have x squared plus 6x plus 4 is equal to ax cubed plus 4ax plus bx squared plus 4b plus cx plus d. Okay, well, now I want to, in a sense, combine like terms. So anything that's cubed I'm going to put together, anything that's squared I'm going to put together, and so on and so forth. So when I do, I only have one cubed term, which is ax cubed. I only have one squared term, bx squared. But you can see I have these x's. So what I'm going to do is I'm going to factor out that x. When I factor out that x, I end up with the quantity 4a plus c times x. And then I have plus 4b plus d. Okay, so this is a little bit different than what I had before. Okay, now what I'm going to do is something that's called equating coefficients. I think there's only one T. Equating coefficients. Okay, and here's how this works. Instead of choosing values for x like we did in the previous problems, what we are going to do is equate our coefficients. Now if we look here, we do not have a cubed term. So that's like saying 0x cubed. Well, I'm going to equate this to this. So this needs to equal this. And the only way that will happen is if a is equal to 0. So equating the coefficients. All right, let's do the same thing with the x squared term. Well, in order to equate these coefficients, 1 must be equal to b. Now, of course, it's not always going to be this easy, because if you look at this, things are a little more complicated. Well, if this coefficient is 6, then that means that this also has to be 6. So I need 4a plus c to equal 6. Okay, well, I know that a is 0, which means c must be 6. Okay, well now I have my last term, which is 4. That's just the constant. These are constants. So I know that these must equal 4. So 4b plus d must equal 4. Well, I know that b is 1, so 4 times 1 is 4, plus d is equal to 4, so I find that d is equal to 0. So I have found A, B, C, and D. Just like the previous examples, now we plug in those values and integrate. So our original fraction was the following. So writing these, I have A is 0, okay, so AX goes away and I just have B. So this is the integral 1 over x squared plus 4 dx plus the integral, well, I found that d is 0, so I end up with 6x over the quantity x squared plus 4 squared dx. You will integrate both of these, and for the sake of time, I think you should do it on your own. You should end up with a final answer of 1/2 times tan inverse of x over 2 minus 3 over x squared plus 4 plus the constant of integration. And that's the final answer. On this last slide, there are a couple of guidelines or hints for solving different equations. So this is like the last step when you're trying to find A, B, C, and so on. So whenever you have the quadratic factors, that's when we equate the coefficients. Otherwise, you have linear factors. You can take some time and read through these. But this concludes all of the information from section 8.5.